Okay, so you are at Rust in Peace, How Bacteria Are Cleaning Toxic Waste and Mining Critical Metal. So with that, I will just say I'm your moderator, Brad Lusk, and I will ask the panelists, starting with Aishwarya, to introduce themselves.
I'm Aishwarya. I'm a PhD student at Arizona State University. I'm getting my PhD in microbiology, and I work on desert rodents and their microbiome.
I am Liz Dennett. I am an astrobiologist by background. My master's and PhD was in astrobiology, specifically how microbes could oxidize and reduce iron, which is not my favorite critical mineral because it's not a critical mineral, but how they could do that as a proxy for life on Mars. These days, I'm the founder and CEO of Biomining company, where we right up the road are using microbes and really sophisticated cloud computing to get more copper out of what is already being extracted from the ground.
Good afternoon. I'm Bruce Rittmann. I'm the director of the Biodesign Swette Center for Environmental Biotechnology. Brad showed you a picture of me with one of my reactors, and he shows some of the reactors. I'll tell you a little bit more about that. It's for recovering really valuable minerals out of wastewaters from mining or ore processing and things like that.
Hello, I'm Cesar Torres. I'm a professor at Arizona State University. I am also part of Bruce's Center for Environmental Biotechnology, and I work on different areas of bacteria interacting with metals. And today I'm going to talk about the environmental part of cleaning the mining waters.
How many of you have heard of the phrase biomining before? A few? Okay. Who wants to tell me what biomining is? Anybody? Using biological material to mine things. So the story starts about 3.5 to 4 billion years ago on Earth, when microbes were first evolving on Earth. And the Earth looked a lot different then. So back on the early Earth, there was no atmospheric oxygen to breathe, right? So life had to find a way to breathe without it. And so the prevailing hypothesis for how life emerged on Earth is in these deep-sea hydrothermal vents. You might have heard about the primordial ooze, so to speak. But these deep-sea hydrothermal vents are ideal places for life to emerge because you are protected from the harmful UV rays from the sun. You have a lot of energy around in the form of heat. And you have a lot of metal oxides that are around that you might be able to eat or breathe. There's also a lot of organic compounds around. Some of the components that make up amino acids are around, which are, of course, the components that make up our proteins. Then you also have a lot of other methane and hydrogen, things like that, that the microorganisms can also eat. So the microbes are able to eat or breathe these metals in a number of ways. So what you're seeing here is a microorganism that is actually growing appendage that comes out of its cell that is electrically conductive, and it is growing out and attaching to a metal that is outside of its cell. And by doing that, it's able to send electrons either to that metal or bring electrons in from that metal. The image that you're looking at on the right, the metal oxide that is basically being dissolved over time by microorganisms that are sending electrons to it or from it, and over time that metal is kind of shrinking and growing smaller in size. Here I have an example of the opposite process happening. So instead of the microbes dissolving this metal, they're actually taking a metal that's dissolved in the water, which if you look all the way on the left, that 0 hour, that red in the water is a material called palladium, which is a highly valuable precious metal. And so that palladium is dissolved in the water. And you can see after we add microbes in there over the course of 2 days, by breathing the palladium, the microbes are able to take that palladium out of the water, which gives you clean water, and convert that dissolved palladium into these solid nanoparticles that are fixed in the biomass. And so these circles that you see, they look like bacteria. Those are bacterial cells. And all those little black dots are palladium they've taken out of the water and fixed in the outside of their cell. So we're able to capture that, harness that. So bacteria are able to do this by often forming communities called biofilms. So on the top left here, you can see a community of those bacteria that have these appendages coming out of their cells. This is kind of them on a glass slide. And if you look on the right, that's a whole bunch of them clumped together into a biofilm with all of those electrically conductive nanowires kind of holding them together and making it easier for them to stick to that metal. We're also going to talk today about how a lot of these microbes are also associated with our bodies. So a lot of you might have heard of the concept of the microbiome. where you are literally as much bacteria as you are a person. So half the cells associated with your body are bacteria and microorganisms, and they are transforming materials, chemicals, food that you eat in and that's in and on your body that can lead to different health outcomes. So I'll close with saying that studying these microbes has been very interesting to a lot of astrobiologists doing fundamental research because they provide us insights into how life emerged on Earth, but also can be used to provide insights on how life might emerge on other planets, exoplanets, or other celestial bodies. And so what you're looking at here is a picture of Enceladus, which is a moon of Saturn, that has an icy surface, but underneath that surface is water, a large ocean that has hydrothermal vents in it. And what you're seeing here is actually water vapor that is erupting through that surface because it's being heated by these hydrothermal vents. NASA has also, they also have evidence that this ocean contains organic molecules, carbon dioxide, methane, hydrogen, the building blocks for amino acids. You guys remember the slide I showed you earlier with the hydrothermal vent, right? So all of those same materials and conditions are on this moon of Saturn. And so studying this fundamental biology has led us to the point where we can start to apply it to cutting edge biotechnologies like what Cesar, Bruce, Liz, and Aishwarya are doing in the lab, applying these biotechnologies to either assist with making more positive health outcomes for humans or assist us in extracting critical minerals, valuable minerals from mining sites, or assist us in eradicating contaminants that are polluting as a result of that mining process. Now I'm going to turn it over to the real stars of the panel.
Okay, so talking about biofilm, Brad introduced us with what biofilms are. They're nothing but a complex community of different bacteria and the products secreted by these bacteria, and there's constant exchange between the bacteria living in that community. And so an example of a biofilm would be when you see slime in your sinks, that's nothing but a biofilm, so it has a lot of bacteria that are growing in there. But basically these bacteria share resources, they communicate, and they have their own little language of chemical sensing that goes on, and that's how they interact with each other in these biofilms. And so think about these biofilms as something like Spider-Man's web, which can provide protection and flexibility. And if that grosses you out, think about biofilms as a city, because it's very organized by these bacteria, and it's basically their home, so that's how they live. So there's biofilms everywhere in the environment, like your sink or in the ocean. They're basically everywhere, and a way to use them is we can have them in bioreactors. So there are a lot of biofilms that can have bacteria that can break down toxic materials in wastewater and basically help you clean your water and make it as a safe effluent in the water body so we don't pollute them. So these biofilms can be SpongeBob and Aquaman's best friends. Speaking of the good bacteria which are present in the environment, here's an example of a plastic eating bacteria. It has these enzymes that can break down plastic. These are the ones that help you clean up the plastic waste. These can be plastic man's biggest enemy. The long story short, with the help of biofilms, if you have one individual bacteria, there's not much that it can do. But when you have a whole team of bacteria, think of like Avengers coming together and trying to solve problems. That's basically what biofilms are. So not just the environment, we have biofilms in and on our body as well. And they can be good or bad. An example of a good biofilm would be the biofilms which are present in our gut microbiome. A lot of these times, these good bacteria help us break down substances and digest things and produce essential things which are important for us. And a bad example of a biofilm in our body would be something that's growing in a catheter, like say Pseudomonas, which is a common infection that is caused in the hospitals. So these biofilms can be pretty nasty and spread a lot of antibiotic-resistant bacteria as well. So the gut microbiome biofilms are basically, they can do a lot of things. And they can also be good and bad. So if you have the good biofilms in your gut, which is why it's really important to eat your fiber and then take probiotics, reduce antibiotics, and so on. But these basically will help us to take care of our health, and they have different signals that they produce. So these signals can even go up to your brain and form the gut-brain axis. So now here's an example. I mentioned I work on rodents and their gut microbiome. Here's a recent study on wood rats. Wood rats are commonly present in the desert here in southern Arizona. And we have trapped them in Tucson. These are pretty cute to look at. These rats have a bacteria in their gut which can break down a lot of toxins such as phenolics and oxalates. So these rats basically eat a lot of creosote bushes and Opuntia cacti, which can have these toxins, basically oxalate and phenolics, which can be toxins. And these bacteria can break down these toxins in the gut of the rat and let them survive the desert conditions and basically help them eat whatever they want in the desert. So all biofilms come with different challenges. They can be hard to control. Biofilms can go rogue pretty quickly if you're trying to tame them. If you're trying to create a biofilm from scratch, if you have even a single contaminant, you don't know what's gonna happen to it. So like Deadpool, they can be unpredictable. You never know what they're gonna do. You want them to break down A to B, but they'll do B to C. You never know. And then scaling it. So a lab-based biofilm would be pretty good on paper, but when you try to bring it to a real world to solve big problems, then it might not do the same thing. So scaling up can be difficult. It's not everything that a biofilm or a bacteria can do, so you might have to do pre-treatments or post-treatments to get to the end goal that you want to reach.
I have the privilege of having a PhD, having spent 15 years in industry, trying to throw my head at very, very challenging problems that hopefully make the world a slightly better place. Today, I'm the founder and CEO of Endolith. You can Google me, you can Google us. Copper is the backbone of modern infrastructure. It's the best non-precious metal material, and we are running out of it desperately. In fact, most extraction mechanisms leave a lot behind. This is a picture of a heap leach. So if you've ever wondered where your copper comes from, this is probably actually from just up the road in the Miami Globe area, but these rocks contain a little bit of copper, less than 0.3%, so a very small percentage. Those rocks are crushed, they're placed in piles as big as this convention center, and those white lines are irrigation systems that spray sulfuric acid on them. So sulfuric acid plus really low-grade rocks means you get half of the copper out. The other half just gets put in as potential acid mine drainage. It gets taken care of and covered. And the thing is that microbes play a dominant role in these processes. They're there, but just like was teed up, when you are dealing with natural system microbes, they can be variable, they can be hard to control, they can be doing their own little thing. And so at Endolith, what we do as a company is we have field deployment containers that are the size of this little shipping container, and we grow microbes on site. These types of microbes, or bugs, as a lot of us will call them collectively, are what are called extremophiles. So they live in extreme conditions. These are a specific type of extremophile that lives in pH 1 to pH 2. So much more acidic than anything you will run into in your normal day-to-day life, much more acidic than your stomach. And they live at temperatures that range from 35 degrees C, the cool end, which is what temperature it is outside today, upwards of 60 or 70 degrees C. And part of the reason for that, they go back to be some of the earliest life forms on Earth. And so they've had billions of years to really take advantage of these ecological niches. So what we do at Endolith is we use tailored microbial communities because biofilms and many organisms are absolutely the best way to go. And we deploy them in the heap while taking lots of measurements and doing some real-time optimization and a lot of DNA sequencing. What that looks like in the lab is we are able to get significantly more copper, about twice as much copper. With existing copper operators and heaps, if we can get 10% more, we are not only saving that 10% from becoming waste, but it mitigates the need for new mines, which typically are very deep, they're hard to find, and in countries that do not have things like anti-child slavery laws. So in terms of the academic scale up, we start in the lab, which you'll hear a little bit more about some lab work here, and that's the hub of pretty much all innovation that happens, is at a lab bench somewhere. We then move from columns to field deployments, and we work with mining customers so that we can provide the adaptive microbes and the heap infrastructure to help them monitor it. So it's a fun dichotomy of going from some of the smallest organisms on Earth that have been around for billions of years and using them as little microbial minions so that we are able to reach our goals of things like stable electric grid and being able to use generative AI to make your life a little bit easier, in addition to having things like wind turbines and electric cars.
So we're going to get to my presentation here, which is about partnering with microorganisms to turn pollution into value. Mining can be very hazardous. You can get, acid mine drainage and other really nasty things getting off into the water supply. This is also true for the ore processing and the recycling. So these are toxic metals that are really dangerous to us and to the aquatic ecosystems. However, those hazardous materials often have a lot of value, provided that we don't destroy the value. So why take a $100 bill and burn it? And this is what we're doing to a large degree these days. But we don't want to do that. So how are we going to stop doing that and turn this into real value? And so we're going to come to the realization that it's bacteria to the rescue. Yes, bacteria to the rescue. And here's our super bacterium. What we do in the Biodesign Swette Center for Environmental Biotechnology, we do environmental biotechnology, which is managing microbial communities to provide services to society. And what are those services that the microorganisms can do for us? I've listed them here: detoxifying contaminated water and other media, capturing renewable resources, and of course also improving our health directly and indirectly. I'm going to talk a little bit about the mineral palladium. We've done a tremendous amount of work with palladium, so I have a lot of information on this. Palladium is one of the precious metals. It's extremely useful in many, many ways in our society. Used in jewelry, it's used in catalysis, it's used in, if you have a gasoline-powered automobile, it's in the catalytic converter, and it's really valuable. So you can see up here, I looked up on the internet a few days ago, the spot price of palladium, $50,000 per kilogram. Now, on the left side, you see a biofilm, and you can see all the little rods and stuff. Those are the bacteria. But you also can see buried in there little black specks. This is palladium, elemental palladium nanoparticles that these microorganisms have produced. So palladium can be, elemental palladium in a highly valuable form can be produced by these microorganisms. But it's not just palladium. We've done a lot of work also with gold. Those behaves the same way. $160,000 per kilogram these days. And then the one everybody in the industry is super interested in is rhodium, $360,000 per kilogram. And our microorganisms can produce highly valuable nanoparticles of rhodium. So how do we do this? Or how do they do it with our help? So we do something called the membrane biofilm reactor. And so what do we have here is we have gas transfer membranes. So here's a picture of some of these membranes. It's like a little bitty straw, about 200 micrometers outer diameter, and are hollow. And we deliver into the center of these, we deliver hydrogen gas. So if you look at the middle here, you can see here's the wall of the membrane, and you can see the hydrogen is being delivered in gas form. It diffuses through the wall and comes to the outside. Now there's water on the outside containing oxidized form of palladium. This is the form that you would find it in water, in the environment. So the biofilm grows on the outside and it oxidizes hydrogen. That means removes its electrons. And it delivers those electrons to the soluble oxidized palladium, and then it produces elemental palladium. Those are the little particles that we saw before. Hydrogen, food for bacteria. The bacteria's favorite food. If you ask bacteria, what would you prefer to eat for your food? And they would say hydrogen. But hydrogen is a very low solubility gas, and you can't really dissolve much in water. So we deliver it directly into the biofilm of microorganisms through these membranes. That's what's called the membrane biofilm reactor. We've done this for all these other materials that I've mentioned and several others. So here's some pictures for gold. So the left one is a scanning electron micrograph. You see the gold. There's the picture on the right. This is one of our reactors. And you can actually see the gold in the reactor. It's actually lining the reactor, the biofilm and some of the tubing in the reactor. So you can see we're producing gold right there. We plated out gold right in the reactor. So we can generate all of these really valuable minerals from soluble pollutant forms using our membrane biofilm reactor and our biofilm communities.
Basically, my topic today, treatment and recovery from mining waters and tailings. I'm a chemical engineer by training, so I look a lot at how processes work, right? How to make something, a series of chemical reactions work. Over there, I have an example on the right of a dust mitigation project that we have where we precipitate iron on top of soils and sands so that we can basically create a frost. We didn't bring those frosts because they break very easily. But it's kind of nice application of metal oxidizing bacteria. We have 12,000 active mining sites approximately in the US right now, and somewhere between 150,000 to 500,000 inactive sites. And you can think of these inactive sites as, when the Spanish came, right? And all centuries of people digging stuff, right? And then in some cases, not in a very good way. In some cases, it's something that happened a few years back and it was a company and there's a lot more work and care of it. But no matter what, every time that you open the earth, you have the issue of mining influenced waters coming in. And creating that propagation cycle that I put there is basically when pyrite becomes soluble, turns into sulfuric acid. The sulfuric acid basically ends up solubilizing more of that iron, the oxidation of iron. It just keeps happening, and then water comes into those mines and creates a problem that needs to be solved, right? So what I want you to think about is that when you're buying a metal and the price that you're buying there of that metal, it's not only the price of mining it, it's the price of maintaining all these mines that really didn't work out. And these companies are still maintaining them so that they don't want to be liable for throwing all this into the environment, right? And so sometimes when we think about these, then you need to look at very simple ways to do it because we don't have 500,000 people to be taking care of this. So typically when you're looking at the treatment and maintenance of these mining water effluents, these are things that are passive and that work, and then people grow a couple of things a year to maintain. So here's an example that we work in the lab in Bruce's center, and that we work in the lab because it's in the field, so we kind of do the studies. It's a sulfate reducing bioreactor. It's basically bacteria doing the opposite of what happened when you open the mine. Iron got oxidized, sulfuric acid came from sulfite. Now the bacteria will take the sulfuric acid and turn it into sulfite. And that sulfite will precipitate the metal, right? And so now you have a precipitation process. The way that we do that is just feeding bacteria, and we often feed bacteria very simple stuff. We like these two a lot, sugarcane bagasse and spent brewing grains. Both of them have something very interesting. One is that it has sugars, and that's good in the short term, but also it has very heavy lignocellulosic material, and that's good on the long term. If you just put sugar, they eat it like crazy and it disappears, right? So you want something that would let them grow quick and then slowly happen, because these reactors sometimes operate for years with what you put on day 0. kind of interesting. This is a picture of a sulfate-reducing bioreactor in the field. But in that system, you see that liquid, and you see that system has a pretty dark orange color. That's the iron precipitating. These mining waters are mostly iron. So this is how we treat it. But you probably learn now from Liz and from Bruce that these mines are not very efficient. These mining waters still have a lot of good metals to be. What we're doing in my lab is using electrochemistry, because with electrochemistry, each metal has its own signature voltage at which it will get reduced and precipitate. And so you can put a bunch of electrodes, and I brought one of my little reactors here that you can take a look at. We put in these reactors bacteria, and the same as we put in the sulfate-reducing bioreactors, so just some lignocellulosic material or other material, and they will make electricity. And that electricity is made by those nanowires that Brad talked about at the beginning. And that electricity is used to reduce these metals. And what we're trying to do that is a little bit more challenging is to have different reactors at different voltages reducing different metals so that we get purity, right? So not just a bunch of random metals. You see down there at the bottom, you have the most precious metals, right? Above the potential of oxygen. That means that these metals don't get easily oxidized by oxygen. That's where the gold, platinum, etc. go. And those are very easily reduced together. And then you have a good window of operation within the water splitting area. Unfortunately, some of the critical minerals that we are trying to recover are very negative and are very difficult to